Today we are going to do section 6.3 on page 689. So let's first see what this is about. The definition of various curves. All right, so the curves has two conditions. First, they are closed or they're simple. Now this thing here is a simple, well, it's a simple curve if it doesn't cross itself. In other words, this thing over here is not simple. And then the second quality is closed. So B is then closed. And so C is not simple, but is closed. D, we don't know what D is, okay? So please do example 6.27 where you get used to considering whether a curve is closed or simple or both or neither or something like that. So let's go to the next page where we consider a connected region. A region is connected in math, well, at least here, is that there's a path that goes from one point of the region to the other point of the region without having to get out of the region. So the path lies entirely in the region that's called D. Now the region is simply connected if now read this definition closely. For any a region D is simply connected if D is connected and it's connected for any simple closed curve that lies inside D. The curve C curve can be shrunk continuously to a point while staying entirely in D. You know what that means? If you imagine a rubber band, that if it's a rubber band that's in D, okay, here's my rubber band, right? And it can just shrink down to nothing. Any rubber band can do that and still stay within D. Now, what does that mean? That means D cannot have any holes, because if it has holes, the rubber band will eventually be stuck on the hole, right? And can't shrink anymore because it has to stay inside D. So if D has a hole, we got a problem. So if D has no holes, then it is called a simply connected region. A region is simply connected if it is connected and has no holes. Now this is, to go into this type of thing deeply, there's a branch of math called topology, which is very exciting. And I recommend that you consider it if you get through calculus and want to move on to more interesting subjects. Although topology is a graduate course, so you might want to take a few college level classes first before you get to topology. But topology is totally awesome. Okay, you worry about shrinking things in space, but that's not the only thing you think about. There's various other things, super exciting stuff to think about in topology. But anyway, let's go to the next page. I'm now in page 691, where you consider a bunch of shapes, okay, whether it's connected or have holes, which means it's not simple, or completely busted into two chunks like this thing. And so let's move on. And we're moving on to look at the bottom of page 691. That's where we're going to consider the fundamental theorem. So the fundamental theorem of calculus, as we have done many times by now, right, is the integral of f of x is equal to the fb minus the big F, the antiderivative f, the big FB minus big FA. Now that is that's called the fundamental theorem. Now remember that, because we've used it so many times that we might have forgotten what the name is. So this is the fundamental theorem part B. There's also a part A, but we'll talk about the part A a little later. Well, you might remember, but if you don't remember, we only care about part B for the moment. So part B. So remember the fundamental theorem, and with that memory, please do example 6.28, which we review some of the concepts we did in the previous section. So I don't have to go over that. Please do that yourself. Example 6.28. And however, I'm going to talk about example 6.28 somewhat right here. Now, in example 6.28, what we have is a function, okay, which is big F, which equals to 2x and 4y, as you can see in there. Now the function is it equals the gradient of the small function, where the small f, the small f function, the small f is equal to x squared plus 2y squared. Now, a quick check of looking at this, you will verify that is true, right? The big F happens to be equal to the gradient of the small f, if you just check the derivatives here, okay? And then in the example, we also provided with some kind of r of t, that is a path. Now, the path is just a straight line, which is 2t, 2t, and t goes from 0 to 1. And then so then as a result, as you can see in the book, you can plug one into the other, okay? That is, you can plug r of t inside big F. Big F is that thing, 2x, 4y, right here. If you plug it in there, then you get plug r of t, the path, into big F, which is right here. Then you get something like this, as your book also says somewhere, right? So big F of the path is the same as the gradient of big F, okay? Remember, big F is the gradient of small f, whereas so the gradient of small f, which is big F, and you can plug the path in there and you get something like this. All right, and that's the end of that example, but I will continue to explore the example a bit more. And what happens is then f of the small f of r t, you just plug in, here's r t, okay, the x position is 2t, that's why I wrote the x here, and the y position is 2t as well. You can plug this into small f, right, and you get, and you add it up, x squared plus 2y squared, plugging that stuff in, and you'll get some kind of a result in terms of t. So the small f of r of t is some function, by the time you crank it out, is some function in terms of t. It's a one variable function because, well, stuff got plugged in there, right? So the small f originally is in terms of x, y, but once we plug in r of t, now it's just a function of t alone. Now, if it's the function of t alone, then we can take the derivative of it, right? Now, to take the derivative of it, we can just take the derivative of this thing directly, which gives to be 24t, or we can do it use partial derivatives. Which is called the chain rule. Now, remember what the chain rule is, okay? This is from page back about 300 pages ago, okay, where the chain, this is on page 406. But you don't have to look it up because I'm just going to show you, refresh your memory real quick. What is the chain rule? The chain rule says that if you have a function of x and y, right, in terms of t, which is right here, okay, x and y are in terms of t, right, which gives us, in our case, we turn it into a path, but it's the same idea. But anyway, x and y is in terms of t, and they are differentiable functions, and z is f of x or y. Then, if you plug x and y into z, right, and then you need to take the derivative, there's the chain rule says dz by dt is partial z partial x. Z is f, so you can also consider that as partial f partial x, dx by dt, plus partial f plus partial f partial y, dy by dt. This should be d. It's close enough. You get my idea. So imagine that's a d. I wrote too many partials here. So because x has only one variable, so it should be d. But anyway, the point is this is the chain rule, okay? And so we can, therefore, the chain rule as, if we follow the chain rule, partial f partial x is f of x, which is, and then x partial t is this thing right here, right? Is the derivative. So as a result, this thing is the same as the dot product. You see, you multiply partial f here, and then dot with the rt plugged in, okay, dot r prime of t, which is dx and dy. Let me write the d here better. It's a d. That's looking worse. And let me fix that. All right, now that's a d. See, much better. And so anyway, this notation can be written like this. It's a dot product, right? You just have these two things and the dot these two things like that. And then of course, when you do the dot product, then you come up to be the same thing, which is what we had before, right? Is where's the, where did it go? Right. If you take the derivative of f, right, that is exactly this, which is what we're doing right here. So I just want to show you an example of all this stuff, just to remind you of what all these notations are about, and also the chain rule. So now that we're ready with that, then we are ready to go to page 693, and let's look at the fundamental theorem of line integrals. Okay, 600, we're on page 693. The fundamental theorem of integrals states that if C is a piecewise smooth curve, so it is at least smooth most of the time, with parameterization R of t, so R of t is a curve like this one, and from some limit a to b, that's fine, and f is a function of 2 or 3 variables like this thing, here's a little f, with first partial derivatives that exist and are continuous, like this thing, right? Here, the first partial derivatives of little f, right here. And then here's the situation. The integral of f dr, which is similar to this. But anyway, we'll look at that in a second. The point is the integral of the gradient of f dr equals to the two endpoints. That is, E equals to FRB minus FRA, which means that this is very similar to that fundamental theorem we saw. Where do we see it? A couple pages ago or something? Yeah, it's very similar to the fundamental theorem that we normally use. See this thing? So the fundamental theorem of line integrals mirrors this particular function. This particular equation, which will make it somewhat easy to remember. The only difference is that you do have to remember that in here is the gradient, which is in a way similar to the fundamental theorem. Okay, is when you integrate is the antiderivative, right? So the gradient is sort of like the derivative of little f. So, well, it kind of is because you are taking partial derivatives to create it. So the gradient is kind of like the derivative of f, and to do the integration, you have to get the antiderivative. That is the original function f itself. So that's how we're going to go about this. Next, let's prove the fundamental theorem for line integrals. Now, first, let's remember what this means, okay, from the previous section, which we did several homework problem. FDR means that it will plug in R of t in f, big F, similar to this one. See, here's my big F, which is that thing, right? You will plug in R of t, this thing, and then dot the R prime of t, and then you integrate dt from a to b, because that's the interval of t, and that's how you calculate the line integral. So we're going to plug our function in exactly like that, except that in this case, our gradient of f is the big F. Okay, so let me write that down. So by definition, we're trying to calculate the gradient of f dr. Now the gradient is, we'll plug it in right into this equation, where the gradient f is the new f, new big F, right? Plugging everything in, so we have the gradient f rt dot r prime t dt, which is fine. Now, the next thing we're going to consider is this equation. The f of rt by dt is this thing right here, which we mentioned a little while ago. See, right here. See, so I rewrote that equation right here, and so you can refer to that for, in case you can't remember what that is. We just presented it. So here is this equation, and then we're gonna notice that this part is exactly this part, right? So we're gonna plug this thing, replace this thing with this. Okay. So now we have the next part. We have the integral of. So the whole equation equals to the integral of a derivative. Now at this point, this thing is just a scalar integration, okay? Because f of rt is just some, see, here's f of our t, is just some one-dimensional, some one variable function with respect to t. Even though it has a vector inside, it's just end up being just a regular function of t. Therefore, at this point, being that what's inside is the regular function of t, we apply the fundamental theorem of calculus, which states that that is just the function, the inside function, okay, that's the antiderivative, right, evaluated at b and a. So then you plug it in. So FRB minus FRA is our answer for the integral, and there, with that we proved our theorem. So that's the slick trick we use to prove the fundamental theorem of line integrals. So what you remember here is to calculate to use the fundamental theorem for line integrals, you just find the original function. If your integral is some kind of gradient, then you find the original function f that wasn't a gradient, and then just to plug in the subtraction on two endpoints. That's it, and then you got your answer. Now let's talk about the conservative fields, which means gradient fields, from the previous section. Now if you're integrating some function, and this function happens to be a gradient field, also called conservative field, which means it turns out to be, there's some function f that is that becomes this thing, okay, that is the gradient of f, becomes the big F, then you can apply this the fundamental theorem and then do your calculation much faster. Now therefore if the function big F is the result of is the gradient of small f, then small f is called its potential function. It sort of works like an antiderivative, okay, and then you calculate. And then you just calculate the integration by simply doing the function FRB minus FRA, like the theorem says. However, notice that while it is true that on our regular function of one variable, where if it has continuous, it always has an antiderivative. Okay, you can always define it. It's the area under the curve. However, for a vector field, things don't always have a potential function, as we have seen earlier. It doesn't necessarily, there's not necessarily a small f whose gradient happens to be big F. In fact, I remember there was a session or two ago, we have some kind of a rule where the partial derivatives, the mixed derivative has to be the same for everything to work out. But we'll consider that later. For now, just remember that a vector field doesn't necessarily have a potential function, okay? And so having said that, please look at example 6.29 and do that as part of your homework. Now, example 6.29, we try to use this new discovered idea of the fundamental theorem. So what we're going to do in there is you're going to calculate something that's called FDR. As always, F is defined as something and C is some curve, right? But what you're going to do is first you're going to do it the hard way. That's part A, where as you can see, and please do this, by the way, because it helps you, it helps something, I don't know. Anyway, so as you can see, you're going to do the derivative the hard way, which means you're going to take the dot product and you're going to integrate, and you're going to do integration by parts, and you grind your way all the way to the end, and we don't mess up one time, okay? Do not mess up anywhere in that big long chain of stuff. Then you finally got to the answer. Or you can do the fundamental theorem, and assuming that the function, the little f, is given to you, which it is in this case, okay? We'll figure out how to calculate little f later. But assuming little f is given to you, you can use the fundamental theorem, which means you simply calculate the endpoints, right? And subtract them. And as you can see, that's just a 3-step project. So much nicer. Okay, so please do this example. What is this again? Example 6. What? Please do this example. I'm missing my page, sorry. Okay, example 6.29 as part of your homework. And then we'll move on. And the next thing we want to talk about is this this, what is this called? Circulation or something. Okay, that is if the circulation of f, right? Remember what is the circulation of f? The circulation of f is when you draw a circle around it. That is, your path C is closed, and then your book likes to sometimes draw a circle around it to indicate the path C is closed. I don't recommend doing that because drawing the integral sign is hard enough. If you have to draw a circle too every time, it's going to wear out your hand. So don't bother doing that. But do remember what it means, okay? Do not ever see a circle on the integral sign and you're puzzled like, wow, what kind of integration is that? It's nothing. It just means C is closed. It's a closed curve. That's it. Okay? So, but anyway, in terms of a conservative or gradient field, where big F is the gradient of some little f, then because if you're integrating over a closed curve, you got right back to the beginning, right? By the fundamental theorem, you just have to calculate the endpoints, but the endpoints are the same, which means it's going to be 0, and therefore the circulation, this closed calculation of any conservative field or gradient field, the circulation is automatically 0 because of this. All right, so let's turn to the next page. So now we are in page 696, where we are looking at the independence of path idea. Okay, now the function big F, when you integrate, is called independent of path if going from the starting point to ending point you integrate. Doesn't matter how you integrate, it's however you get there, the integral end up being the identical. If that is the case, it is called independent of path. And as a result, if f is a conservative vector field, then f is independent of path. That's the theorem 6.8. Now, theorem 6.8 is quite obvious, actually, because being that if the f is a conservative, that is a gradient field, it comes from the gradient of something, which means which by the fundamental theorem that we just covered, you just calculate by endpoints, but they start and at the same point, right? So then the integral end up being the same. So that's all there is to that. Now, so let's look at the next page. All right. Next, let's go to page 697, where we're going to prove theorem 6.9. If a function is independent of path and the domain is open and connected, then the function is conservative, that it is a gradient field. This is the most exciting theorem in this section, so let's have great fun with it. Now, to start with, let's figure out what we're talking about. The domain is, f is a continuous vector field that is independent of path. That is the big critical point. That is, if you do the FDR from one point to some other point, and it doesn't matter how you get there, okay? The integral will end up the same. The condition is that domain D has to be open and connected. And but it doesn't say it has to be simply connected, so holes are acceptable, which is why I drew a hole here, which although your book's illustration doesn't have a hole, I thought a hole is nice to remind you that having a hole is okay for this theorem. Now, if every path, if that situation happens, that is, the path is independent for this field, then this f is a gradient field, or also called conservative. So path independence is one way to test it. If you can get there, and yeah, it doesn't matter how you get there, the result of the integral is the same, the FDR, that is. And so, so how are we going to prove this? Now, first, for now, we are only going to prove for the two-dimensional situation, okay? That is, we only have, the big F has only two variables. We call it P and Q. Now, here's how we're going to do this. First, in the domain, we're going to fix some random point. Doesn't matter where, really. And then we'll fix a random point, and we'll call that point X, okay? So X does not move. next we're going to consider some other point xy that isn't on x itself, okay? So any other point xy, we are going to call it define where, well, there's a random point xy, and we are going to hold y constant for the course of this story. So y is constant, but x moves. I mean, we consider x as a variable. Okay, that's what we're trying to get it to move. And anyway, so the first thing we're going to do is define function f(xy) equal to integral f dr. Now, this is not to be taken lightly. The reason we can define it, where c is any path that goes from the fixed point x and our whatever point that we're thinking about xy. Okay, the whole c will be so f of xy in some other point is a function that's defined that way, and we define it this way for every point in the domain. Now, this is not to be taken lightly because the only reason we can do this is because it's path dependent. That is, doesn't matter what c is, we can the answer will be the same because we have, that's the big fancy condition, right? This field is independent of path, and so your function makes sense. Just pick any c, okay, and get from big X to wherever you're supposed to go, and do the integration of f dr, and then that gives you the function. It doesn't matter what c it is. If it isn't independent of function, then independent of path, then this function wouldn't make any sense, okay? Because it gives a different result depending on c. So what's it supposed to do? Nobody knows. But being that it is independent of path, we can totally do this, okay? Just any c will do. It will give us the same answer no matter what path c you pick. All right. So then, so now we got our f(xy) defined, and our goal is to prove that the gradient of this function will be the big F. In other words, then big F is a gradient field because there exists a function at small f whose gradient it becomes the big F. Okay, so then big F is a gradient field. It's conservative, also called conservative. All right, so now that we have our little function, what are we going to do with it? Well, first let's look at our little function. So here is what we're going to do is first we remember that domain D has to be open, which is fine. And that means we have a little area in here. Okay, so we're going to draw the path, pick a path where it consists of two parts. Is independent of path, so we can pick any path we want. So we're going to go from S, we're going to draw a level line, that is with y being constant. See, y is constant in here. We're going to draw a level line from xy so that it goes to some other space called ay, okay, which is still inside the domain. And just a small enough section so that it stays inside the domain. And then, so we'll go across like that. And then, so that part, just a small level part, and then the rest will continue to go whichever way to x. So we have so our path C here, right here, is defined by two paths, C1 and C2. C2 goes from the a comma y to xy. Remember, y is held constant during this proof. We don't care to change y. Okay, we are only going to change x. And with me, I increased a small amount of x. That's also level. Okay, everything with y constant on this straight line, and I call that delta x. Now, so C2 then is called we can represent it, the C2, this level line here, straight line, as a ty. Okay, remember y doesn't change. And so then where t goes from 1 to x or something like that. And then our prime of t is then equals to 1 comma 0. Now the reason this is 0 is because y is a constant as far as r is concerned. Okay, we're not going to change it. That's why the derivative of prime, being that is just a level line, the derivative is 1 comma 0. All right, so that's that. So the next thing we're going to consider then f of x and y then is consists of two parts, right? Because then it becomes the sum of the integral of c1 plus c2 because we define c as the two-part section. Now the next thing we need to calculate is what is partial f of x, that is partial f partial x. What we're going to do is, the book said something that I don't quite see, so I'm going to directly prove it, okay? And what we're trying to prove is this thing, but so I'm going to prove it directly instead of just say something. And so the partial derivative of f of x, by definition, is x plus delta x. Here's my delta x right there, okay, a little bit, a very small x. You just push over a little bit, plus delta x, okay. Y holds the same, so minus f of x, okay, with y tagging along, and divided by delta x. That's the definition of part of the partial derivative, which if you plug it in here, then you get this thing, okay? This is the first part, right? Because it equals the two sections added up. This is the second part, just f of x. This added delta x. But when you subtract it, you notice that c1 is gone, okay? c1 is gone, and so that your f of x is only dependent on c2, right? Is c2 plus delta x and then minus by c2 and divided by delta x. That will be the partial derivative, which is the same. This is the same as saying, being that it doesn't depend on c1 at all, then because it got subtracted out, this is the same as saying the partial derivative of just c2, actually. So we take, and that's how this makes sense. So anyway, the part of the reason that's true is because C1 is clear over here. You know, it doesn't really necessarily affect the partial derivative of this particular point. And that's why we do it this way. But I feel that this is a more clear, definitive explanation of why that is the case. Anyway, so the partial derivative of f depends on C2 only. That is, and when I say that's the partial derivative at that point, see, where, anyway, so now that we know that, we are going to remember that r of t is t comma y, right? And then we're going to plug stuff into this thing. Now, when you plug it in, then we have, we will, please look at your book on the page, right? First, we have, we'll plug in the formula FDR, which is FRT dot R prime dt. And then what is R prime dt? That is the derivative of R of t. R prime of t is this thing, which is 1, 0. So we'll fit that in there. So the derivative of, that is R prime of t here, is just 1, 0. And when you dot 1, 0, then you get a very neat answer. That is the first part of f. Is partial derivative of, remember what f is. F is p comma q, right? So the x component is just p. So then when you do the dot product, then you have just t. It becomes just the p part, the x component, which is p of t and y. Now let's look at this. I should have written down further. Is f is defined as pxy qxy. If you plug r of t, where is it, right here, into p, where x is t, right, y is just y, so then f of r t is pty qty. So when you take the dot product of, if you dot it by 1, 0, then you only got the x component left, which is pty, and that's where we got this thing at the very end. See the partial. So then, so fx is now, so far we have come down to that part. So far so good. And next, let's talk about the fundamental theorem of calculus. Now, here's the fundamental theorem of calculus from Calculus 1. This is Part A. Part A states that if f of x is equal to the integral of from a to x of ft dt, then f prime of x is equal to whatever is inside. Okay, that is f is the antiderivative of little f. Now, in that case, if you apply this principle to pty in such, where y is just some constant that tags along, okay? So then by this same principle, then f prime which is partial x of this thing, is the same as what's inside. See, the same principle. The derivative of the integral is just what's inside. See, so the derivative of this integral, it is what's inside, and you plug x back in. See, and it's completely the same. And as a result, then we have the last point. The final equation then is f of x is equal to pxy. That's the final result, as that we have seen right here. Now that means that, so what have we been doing? We have so far from beginning go all the way down and prove that f of x is equal to pxy. So then if fx, so let me get back here. Okay, so here's the function f. So we have proven that for the small function that we defined right here, this thing, it has a quality of fx is equal to this part, okay, pxy. And then similarly, being that there is no reason for us to do x, we could have done y the same way, the other partial derivative. Similarly, so fy is then equal to the other part, is equal to qxy, which means the gradient of f is equal to the big F. Okay, that means that big F is, the small f really is the potential function of the big F. So that concludes our proof, which is if the function is if the vector field is independent of path, and with the domain being open and connected and stuff, then f is a gradient field. That is, there exists a small f whose gradient equals the big F, and that concludes our proof. Now, having said that, now let's being that conservative or gradient fields have the quality of being independent of path, to show that a vector field isn't conservative, one way would be to pick two paths, two easy paths preferably, and then do the integral and show that they're different, which is example 6.30. And please do that as part of your homework. Next, let's look at page 700, where we have there example 6.31. How are we going to find the potential function? Well, the potential function actually turns out to be pretty easy to find, lucky for us. What you are going to do is that you are going to come up with some small function f, whose partial derivatives are going to be equal to the two parts of the big F. So then what are you going to do is you know that small f is you're going to integrate, okay? Being the f, for example, like this. If fx equal to the big function is 2xy cubed, etc. So the small function with respect to x equal to 2xy cubed. What is the small function? Well, then you integrate with respect to x, okay? So that you get x squared. Y cubed, and then plus some function of y. It's important to remember that that function of y has no x in it, okay? And then you take the derivative of this thing with respect to y or something, and then that gives you something else. And then you compare the two, and things come out right away. Yeah. And anyway, so then you can find the potential function very quickly as a result. For details, please do the example 6.31, and that'll make sense. What happens is mostly, well, actually, they even have as procedure listed at the bottom of the page, how to find a potential function. You just integrate, and then you differentiate, and you compare the stuff, and everything will come out nicely, okay? And so please do example 6.31, and then example 6.32, as part of your homework. And then, example 6.33, same thing. More examples of how to find the potential function. You basically integrate, and then you differentiate and stuff. Anyway, finding the potential function is easier than it sounds, okay? It's easier to do it than for me to even explain it. So let's move on to page 703, where we have a theorem of how to test conservative fields. And let's move forward to theorem 6.11, where it says that if f which is denoted as PQR, is a vector field in an open, simply connected region. Okay, at this point we require it to have no holes. So that's what simply connected means. So open, simply connected region D, then those three things will have this equation where Py equal to Qx, we're talking about partial derivatives, Pz equal to Rx, and Qz equal to Ry. And that's for 3D situation. This is true if and only if f is conservative. The if and only if means that the implication goes both directions. That is, you have two sentences combined into one. That is, if the fact stands that that is, if Py equal to Qx, etc., then f is conservative. The other way says, if f is conservative, then Py equal to Qx, Pz equal to Rx, and Qz equal to Ry. See, so that the implication goes both ways, which means these two conditions always happen together with no exception. And that's what if and only if means in English. Now, remember that at some point before we have already mentioned something like this. That is, in the 2D space, then if f is just PQ, then f is conservative if and only if Py equal to Qx. Well, okay, maybe we didn't mention this exactly, just part of it. Something about if it's conservative, then Py equal to Qx, something like that, and which we did a little bit of homework before on that too. So let's go to the next page, page 704, and example 6.34, and where you determine whether some vector field is conservative. Well, you do so by figuring out like Qz, the partial derivatives, and check if they're equal. If not, then it's not conservative. The same as example 6.35. And then next, let's look at Next, let's look at the bottom of page 704, where we have this interesting function where the cross property does work. Okay, it's something about Py equal to Qx for this fairly complicated looking function right here, right? Py does equal to Qx if you were to check. However, if you are to check some line integral around various paths, you will quickly find out that, let's look at the next page, you will quickly find out that it doesn't equal. Okay, that is, in other words, the field is not conservative, even though it has the quality of the partials being equal, the mixed partials being equal. The reason for that is because this function f is not defined, its domain is not simply connected. Because for that, remember we mentioned that the domain has to be simply connected for that trick to work. And in this case, being that this thing's domain isn't simply connected because there's a hole at the origin, okay, because it's dividing by x squared plus y squared, which means it's not defined as 0. So there's a giant hole there. In fact, the function probably, the function does something, okay, it goes nuts at 0. So as a result, then this function is not conservative. Okay, because the requirement that domain has to be open and simply connected is important, the simple part, no holes. For the Qx flipping the partial derivatives to work. So then please do example 6.36 as part of your homework, where this time we're going to use the fundamental theorem for line integrals. So then we are going to calculate things, and things tend to be very, very, very fast to come by once you come up with a potential function. Okay, and so that's that. And next, please do that. And then example 6.37, the same thing. We will calculate some work or something, and we'll use the fundamental theorem to come up with a potential function, which will make life much, much easier. And that comes to the end of this section. Now for homework, please do, on page 708, please do problems, let's see, there is a big long description. Anyway, so 708, please do problems 105, 107, 109, 113, in problem 113, ignore the circle on the integral sign because it's integrating along just some regular path, not a closed curve. But it stuck your book stuck a circle on it anyway by mistake, I guess. So ignore the circle. And then 117, 119, 123, 25, 29, 35, for which the answer in the back is wrong. 137, 141, and 141, the answer in the back is also wrong. So what I did is I calculated, we're supposed to calculate this thing. I calculate this thing directly with by the method from the previous section and calculated with what we learned today. That is, where is it? I erased it. The fundamental theorem, which is much easier. So please do 141, problem 141 two ways. And then when you're done, I want to talk about it somewhat. And now that you're done with the homework, let's talk about it. Problem 137, I guess is fairly straightforward. Okay, now we just you plug stuff in, you follow the formula, and I guess you find out what f and y what the potential function is. I found it right here, and then you plug in the numbers, and out comes some kind of an answer, and turns out to be correct. So that's that. Sorry, what I showed you just now wasn't 113, or did I show you? Yeah, I must have showed you 137. Well, 113 is the same way, except here easier. You there's the integration. You find out f x, y is, which for this problem is very short, and then you do the plug in the fundamental theorem, and out comes your answer, which is correct. Okay, problem 135, the same kind of deal, right? We have a function, and then we need to find the potential function by messing around with the partial derivatives. And then eventually I was able to hunt it down right here. And I also double checked, so this is correct, okay? That is, here's the, let me show you how I hunted it. Well, it's just a straightforward process, and I came up with the small function, the small f function, which is the potential function. And then I used the fundamental theorem, which got me this, and then eventually ended with the answer of 159. The book gave the answer of 150, which and after a lot of checking and stuff, I'm positive that I'm right and the book is wrong. Maybe they typed the last digit wrong, see? But anyway, so here's what I did. What I did is I typed it into the function evaluation calculator. The link is below the video, in the video description. Here's what I typed it in, okay? Just to make sure that I didn't mess up somehow. And as you can see, we're supposed to evaluate from 4 to 1, right? So as you see at the bottom, the calculator says the evaluating that big complicated thing, please practice typing this thing into the calculator to make sure you know how to do it. So here's this. So once I typed it in, and then it's, see, for 4, it comes out with 160, and for 1, it comes out with 1. So when you subtract it, it's 159, just like I said. So after I've done that, I feel confident that I must be right, and the book must be mistaken. Maybe it's a small typing mistake. So that's 135. Now, I already showed you 137, but I will show you again, just for no reason, okay? In case, so that is 137 is just a straightforward matter of finding the potential function, and then you apply the fundamental theorem. And then finally, problem 141, okay? 141 is similar. That is. Anyway, we have given the function, right? We have to find, here's the path. We need to find the potential function, which is that. and then I need to plug it in so that do the subtraction, for which I got 2.99. That is a very, very different from what the book has, okay? So I stared at it very carefully. This problem doesn't really look that bad. And then, so I wasn't sure where I might have gotten it wrong. But after very careful checking, I could not find anything wrong with what I did. So what I did is to confirm that I'm right and the book is wrong, I redid this problem the old-fashioned way. That is, I did the dot product, okay, which I ask you to do as well. That is, without using, that is, we do it with the same way that we did in the previous section when we didn't know the fundamental theorem, so therefore life is a bit harder. So to do that, what I did is wrote out everything, right, and follow the theorem from the previous section, which is means you take the dot product, and that end up being too long. Check this, being too long integrals, right? But they're definite integrals. And then I typed it into the calculator, and which the top integral ended up being 4 point something, the bottom integral ended up being -1, and I ended up with the exact same answer by doing a completely different way. I got the exact same answer as I got using the method of this section. So when I used the method from the previous section, so that's why I feel that that I have to be getting it right, see, because these two methods are completely unrelated. Now I want to show you how I did the integration, okay, on the calculator. I used the Wolfram Calculator. I normally use the Symbolab calculator because it's kind of easier to use, but this looks like a very tough integration, so I didn't even bother with Symbolab because they have a hard time doing anything that's slightly difficult. So the Wolfram Calculator is a little bit harder to use, but it does work better. You know, it is a more powerful simulator for integration. So here's how I did it, and I would like you to do the same, because I want you to type this thing into the calculator, and then in fact, don't even look at how I typed it. Try to type it in yourself, okay? Figure out how to do it, and if you have trouble getting it to work, then look at what I did so that you can get it to work. Because you know I got it to work, so you know it works. So you see, I typed the equation in very carefully, okay? Everything has to be exactly as is. I don't know, let me zoom in a little bit here so you can see it even better. All right, that should be close enough. All right, so you type the equation in, both equations. Here's the bottom, there's the second equation. I split it in two so that it's easier for the calculator to handle instead of having a big long thing. So now we have two still pretty long thing, but somewhat better, okay? And then to do the integration, first you will pick the definite integral, okay, which means you click the star tab up there where I circle red, and then click the definite integral tab, which I also circle red. So then you can enter in. As you can see, you can integrate with respect to t, okay? This thing is very smart. It can you can do t as well as x. And then after that, when you type it in, to type in the pi in here, you see the tab on the other side of over here where I circle the square root sign. If you click that tab, then the pi will come out, among other things. So you can type the pi in there, and then calculate your integral. And so as you can see, once I did that, the two integrals calculated to be one to be to 4 point something, right? And the other one down here is -1. So when you add it together, it's the 2.99 answer that I came up with. So that's how I confirmed that. That's how I feel confident that I was right, and the book has to be wrong, because I did it with two completely different methods and came up with the right answer that's different from the answer in the back of the book. So anyway, it's a nice experience to go through this, okay? Because typing these things in, I actually messed up a little bit. I think I forgot a parentheses or something, and the calculator says, I don't know what you're talking about. So you have to be very careful, make sure everything comes out perfectly, and then the result will come out. And that marks the end of this section.